Welcome back, everyone. So this is another part of or a continuation of our previous discussion, going into a detailed analysis of inverters and the modulation voltages, and we started talking about the different voltages and how they are related to the phase voltages, right? And then last time we stopped after deriving this relationship, very nice relationship about how we can actually relate the bridge voltages or the modulated voltages from the inverter to the different phase voltages. Okay, and then we are going to use this in the coming couple of pages in our discussion on how these modulation strategies work. Okay, so before we go ahead into our discussion, I do want to go over a little bit of how the PWM modulation works. I think we talked about this in the video before the last one. And, we have this carrier wave, right, which is at a very high frequency, typically, 10, 20 kilohertz frequency range. And then this is our modulation or the reference that we use. Typical, I mean, it's even slower than what I'm showing here, because if you're modulating a sinusoid, then you have to be at least, 10, 20 times in terms of frequency. Your modulation frequency has to be 10, 20 times higher than your frequency modulated frequency, so that you rebuild your the waveform that you intend to build, especially if it's a sinusoidal or an arbitrary waveform. And we said that we have, depending on how the comparator is set up, you're going to generate a PWM signal that is applied to the inverter. Okay, so that PWM signal will actually determine what your VAG voltage is. If you are to look at the instantaneous voltage, your VAG will either be on or off if it's a PWM fed inverter, right? And then these are depending on how the comparator is set up to generate that PWM. Okay, this is a triangular wave. We looked at the ramp, the sawtooth as well. Sawtooth, yeah, the ramp, right. So this is what you're going to see at VAG, right? So this is modulated based on that wave that we apply as a reference. And this DA, this is going to be the duty cycle, and this is a more generic term. You'll see that DA is a sinusoid or a cosine wave, depending on how you want to modulate your output. Okay, and now, so with PWM like this, it's a little bit difficult to analyze. So what we are considering is a filtered version of VAG for our analysis. If you are to look at in the frequency domain, typically, your carrier frequency will be somewhere up here, whereas, your the waveform, the sinusoidal reference is somewhere going to be here. So without losing any information, we can assume, we have a low pass filter to remove the high frequency content, and that way we have an average signal. So this hat represents that filtered or the averaged out signal to simplify our analysis. So basically, from this point onwards, even though it's a PWM inverter, the voltage that we see is called a fast averaged signal, where it looks like it's following a sinusoidal nature based on what we apply, right? Following the duty that we apply. Okay. All right. So our duty here, we are considering a duty that varies from -1 to +1. And then depending on the duty, we are going to see 3 primary states, and then of course everything else is going to be in between. If we are at 100% or 100% duty, which means at 1, right? So this reference is all the way to the 1. What we'll have VDC, full VDC, as the average voltage, because your pulse width, or your yes, for that period, it's going to apply full VDC. Okay, and then if you are at negative 100%, that means this waveform is all the way at the bottom. Okay, the red waveform is all the way at the bottom. That means this is going to be what? It's going to be -1, right? -1. That results in a fully off signal for the full period. So you will have 0 volts, 0 DC, right? When you average it, you're going to see 0 volts at the output of the bridge. And if you are considering 0%, that means right in the middle, right here, right? So this red waveform is right in the middle, and then that will result in half the DC. So the point I'm trying to show you here is we are getting a voltage that modulates between 0 and VDC. It's going to vary from 0 to VDC, VAG. With respect to ground, the phase A voltage. Okay, not neutral, ground. Okay, so that's the primary idea here. Now, if you look at all 3 voltages, you're going to see, VA, VAG, VBG, VCG, they will have their own duty cycle, right? And these are going to be balanced and 120 degrees out of phase from each other. And then each will have its own modulation level, and you'll see that in the coming pages. Okay, so we have our VAG, VBG, and VCG for this case, right? For now, let's assume DA, DB, DC are left as they are, untouched, but we want to see what our phase voltage is. The phase voltage, if let me try to remind you what that is basically from the inverter. If this is your neutral point, right? So if this is your neutral point, we said this is my phase voltage, VX. This is important because this is what the machine sees. This is how the motor, that's what the motor will use for its operation, current, stoke generation, and all that, right? So we want to identify, though we apply this VAG, what will be truly applied to the motor phase. Okay, so in order to do that, we have to be a little bit creative in trying to analyze that. If you remember, at the end of the last video, we kind of left off with this equation, right? We left off in that equation, and since we are considering fast average signal, or those filtered signals that we are considering here, we can convert all of the signals to be fast average because all of them are PWM'd. Therefore, it's valid to say that we can even consider the relationship to be valid at the fast averaged case. Okay, so we have the fast averaged case, and we know what VAG, VBG, and VCG are going to be. DA, DB, DC related components, right, from the previous page. So let's substitute. I do need to do some work, so I went into a different pen here. So we basically substitute the individual components, and then we have this nice little relationship. However, I did add a DA, an additional DA, and subtracted that DA out. Okay, this is going to be very useful to us. Now, when we look closer, we can now see we have 3 times DA, so 2 DA plus this new DA, we have the 3 DA. Now minus, we have a minus DB, minus DC, and I have a minus DA. So that makes up what? A balanced set. If DA, DB, DC are sinusoidal and are balanced, then this will go to 0. We call this the 0 sequence relationship, right? So this will go to 0. So with that, we are left with this following relationship for VAS, for the phase voltage that applies. Okay, so in this scenario, if we apply a balanced sinusoids dA, dB, dC, then that will directly reflect on VA, VB, and VC. Okay, and depending on what our dA, dB, dC is, let's say we apply a cosine waveform, right? A cosine with the amplitude being 1, you can only reach a maximum of half DC, VDC by 2. So this is that sine triangle method that we spoke about earlier. Okay, in our couple of videos back, we talked about the sine triangle method, right? So if our modulation, about our duty is with constant amplitude and cosines or sines 120 degrees out of phase, VA, VB, VC are going to be balanced, and they are going to be half of our DC bus voltage. Okay, half of DC bus voltage. Now, let's go to our VAG for a little bit. Let's see, where is my VAG relationship? Now, from our VAG relationship, right, we can see that we can only reach 1 here, right? We can only reach 1, because if we try to go beyond 1, we are no longer able to reach anything beyond VDC, because that's the maximum point we can reach in terms of a DC bus. Okay, and this is true when we have this sine triangle modulation. Okay, so in the sine triangle modulation, we are limited to applying half our VDC to our phase voltage. Okay, now, can we improve upon this? Can we do something better? Yes, we can. Okay, so I don't remember exactly who came up with this idea, but there's been a proposal long time ago, of course, to inject a third harmonic component. See, this is 3 times theta c, the converter reference frame, right? Converter reference frame. So basically, this is omega c times t. You're going to have some kind of an electrical frequency, right? So therefore, this is omega c times t. So it's 3 times that. So it's a third harmonic. So we call this the third harmonic injection, but to duty, to nothing else, to duty, right? Now, when you do that, what we'll have is, so these are our VAG, VBG, VCG relationships, right? And then basically you take this dA and substitute them to our VAG, VBG, VCG equations. Okay, so that's straightforward. And what I want to look at in this case is look at my neutral point. Okay, the neutral point. What does the voltage on the neutral point look like with respect to ground, with respect to our DC bus ground? Okay, so let's try to do that here. So let me, okay, so now in order to look at the neutral point, and we've seen this relationship before, we can use the sum of VAG, VBG, VCG, right? We can consider that for our neutral to ground voltage. And now we can substitute VAG with the third harmonic injected component for all 3 actually. And we can look at this relationship. Okay, it's a little bit lengthy. I mean, not that bad, but it's lengthy. And you can see that your neutral point voltage with respect to ground has a third harmonic component. It is oscillating. It's being modulated. Not as fast as your PWM modulation, but at the frequency of the third harmonic. Okay, so that means as our 3-phase sinusoids are applied, the neutral point voltage is varying at the 3 times frequency of that. Okay, that voltage is fluctuating. So, and it's so third harmonic injection is a little bit of a difficult concept to visualize, but I'll try to use some simulation and plots here to show you what that looks like. But basically, the idea is your neutral point voltage is no longer fixed. Okay, your neutral point voltage is, it has that third harmonic component. Okay, third harmonic component. Let me see. In our previous discussion, did we derive a VNG relationship? I think we did. Yeah, so that's 1/3 of VAG, VBG, VCG, right? We came up with that. And the only difference here is we have that third harmonic component on the neutral point voltage. Now with that, we want to see what our VAS is, okay? Because it's a little bit different from the previous case. Let's see what our VAS looks like, okay? Now, to our surprise, when we substitute this neutral point voltage, what we will get is phase voltages are going to be the same, right? So VDC, here we are going to see VDC by 2D cosine theta C minus 2 pi over 3. And here VDC over 2E cosine theta C minus 4 pi over 3. Okay, so it's, if you look at our VAS, VBS, VCS, we are still seeing the same voltages even though we are injecting the third harmonic component. Then, so why then is this useful? Okay, so that's a good question. So in order to answer that question, I want to switch here to my simulation. At least I have a very simple plot that I can share with you. Okay, so in this plot, I'm showing you 3 sets of waveforms here, right? So the blue waveform in this top figure, this blue waveform, okay? Let me see if I can grab a little. So that waveform, okay? That's basically my d cosine theta. No third harmonic component, just that voltage as it is, d cosine theta, right? Like we would do sine triangle modulation. Now, the red, or if you want to call it the pink or orange, right? This is the third harmonic component. That's the third harmonic component that we are going to inject. It's 1/6 amplitude. Okay, D3 is 1/6. And when you add the two together, when you subtract the third harmonic from the original cosine waveform, right, which is still a third harmonic injection in the frequency domain, if you think of it, you get this yellow waveform. Okay? So what it's essentially doing here is that at the peak of the waveform, the third harmonic is pulling it down a little bit. So you can see that when we are reaching the peak voltage, the third harmonic injected component is not reaching the peak voltage yet, right? And then this is true for phase B. So here you can see this is phase B. This is without third harmonic injection. This is the same third harmonic as before, right? And see what it's doing. It's pulling this down, and when you actually add the two together, your phase, your VBG, third harmonic injected VBG, looks like that, right? It's not reaching 1, so you are not hitting the full VDC, even though your modulation in your sine triangle case, it's reaching that max. Your rho sine wave is reaching that, right? but the third harmonic component is pulling that down slightly. Okay, now, so what, right? So why do we care? So the interesting part is when you look at the phase to phase voltage, when you look at VA, so when you look at VAS, which is, if you recall, we used the inverter voltages VAG, VBG, VCG, and we computed VAS based on a combination of those, right? Even though VAG, VBG, and even if you compute VCG, it's going to have this third harmonic injected component. But when you add 2/3 of VAS minus 1/3 of add 2/3 of VAG, 1/3 of VBG, minus 1/3 of VCG, you're going to get a sinusoid, which is your VAS voltage that you apply to your machine. That's what the machine sees. Okay, this is the phase voltage the machine sees. Now, why is this advantageous? This is advantageous because our VAG hasn't reached the VDC bus yet. It hasn't reached 1 yet. However, our VAS is at 1, which means if you increase, if you can somehow increase the modulation index. So right now, if our D is 1, right, you can increase the D to be slightly more than 1, maybe 1.1. You are able to provide VAS more than half your DC bus voltage. More than half your DC bus voltage. If you remember from our previous case, we were limited to half VDC, right? But in this case, we have more room. See, we can, this is our D, the total modulation, right? We have room here to increase our D so that we can get the phase voltage to increase slightly. So this means just by adding the third harmonic component, you can supply a little bit more voltage. I believe it's 15% more voltage than the regular sine triangle modulation based case. Okay, so that means you can get more voltage in, and you can go to a higher speed or provide a little bit more current to get improved performance from your drive stage. Okay, so there is an advantage in doing third harmonic injection because now you can reach slightly higher phase voltages, Okay, now in practice, of course, you can inject third harmonic component like we just did, right? But there are more practical schemes that people use in industry that you'll see, when you look at code and algorithms that are implemented. And let me show you one such simple implementation. So essentially, your third harmonic component ideally is going to be a sinusoid or a cosine, sine or cosine, right? Instead, so if let's say this is our third harmonic component. Okay, this is our third harmonic component. Now, what's happening is implementing sinusoids in a computer is a little bit more costly because you take up memory to store the tables, access the tables. But instead, we're going to approximate it. We're going to use a triangular wave here. Okay, so by doing that approximation, you can achieve very similar result as third harmonic injection and you're sacrificing a little bit more harmonic content because it's not a pure sine wave. Like a triangular wave is not a pure sine wave, so you are going to see a little bit more harmonic content in your currents, in your voltages, but they're not as significant as the cost saving you get by approximating to this triangular waveform. Okay, in frequency domain, you can compare the two and see what kind of benefits you get, and typically it's very beneficial, and you save a lot in processing memory when you implement the triangular wave in a system. Okay, so just to summarize, in this one we went over the different modulation technique, not all of them, but at least laid the groundwork to mathematically represent what VAG will look like if you have a PWM modulation. What are the boundaries you see? What's the peak voltage or phase voltage that you can apply? And then with third harmonic injection, how much of an improvement can we obtain? Right? So we looked at all those things here. And with that, I'm going to wrap up this session. Thank you.